Okay, so yesterday we decided to start the last part of the course and search for our electrons. Okay, remember the goal of the course was to describe quantum electrodynamics, which is a theory of the interaction of electrons and positrons with photons. We realized that we were missing a big part of it because we didn't have the electrons. So we set out to look for them. We didn't know if we were going to find them. So we just decided to go and try to classify all possible theories. So one that was missing was the theory using the spinor representation of the Lorentz group. We discovered that there are two spinor representations, the left-handed spinors and the right-handed spinors. We constructed Lagrangians. The Lagrangians we discovered had to be massless. So they didn't look like very good electrons to us. We then decided to put them together, and putting them together into a single object, which is called the Dirac spinor, gave us a theory that has what it looks to be a parameter that looks like a mass term. So, but we haven't actually proven that this M has a right to be the mass. Okay. We also introduced this fancy notation to denote the contraction of the derivative operator with the gamma matrices. And today we're going to be using the Dirac basis. Yes.
Like both the Peskin book and others, that's the wild.
This is a wild basis, really?
So the wild basis is the one where gamma 5 is diagonal, right?
Is gamma 5 diagonal in this basis?
Yeah, because you've got 4 multiplying, right? And they're all off diagonal, so...
Yeah, it's strange. So but the one we got before, so the one that we got straight from the, no, sorry, the one that we got straight from the, oh, I see. When we multiply by beta, then they switch. I see. So for some reason, so this one is exactly the one that you get from the derivation we had yesterday, when you multiply the alphas by beta. So that's what you get. I see. So, well, it's just a name, but I well, it turns out that for what we want to do today, this one is actually nicer. I see. Sorry, are you sure?
Yes. I just double-check right now.
Oh, okay. So, do you have there the Dirac basis in your? Oh, I see. Right. Because when I multiply with beta, the alphas that we had yesterday, then they switch places and they become exactly this. I see. So this is just a. Oh, I see. So somehow I didn't put it in my notes. I see. Okay, that's fine. Okay, very good. So let's use this basis. After all, it's just a basis, and it seems to be fine. It seems to be nice for the purposes that we're going to use now. Okay, so what do we want to do with this? We want to solve not in the Dirac spaces, but in the Pi basis. So, well, that's life. So what do we want? We want to study plane waves. So as usual, Okay, so I don't remember if this was the plus or the minus. Let's call it plus, okay? Let's take just this part. These are solutions with positive frequencies, so let's just take this part and study what this has to be. This is a 4-component object, because of course this was a 4-component object. So if you wish, we can give an index. So let's say that we have indices A and B that go from 1 to 4, okay? So our gamma matrices also have indices A and B. Those would be the components. And there is an index A here, and there will be an index A. But as a vector, or as a 4-component object, we can just write this, okay? Very good. And I just realized that who said that string theory wasn't useful? Now I can pull down. Strings are useful, especially the open ones. So thanks for the little technical improvement to the blackboards. Okay, so that was.
How is U a 4-component object? Because it depends on the K.
Okay, let's make it a 4-component object explicitly. Now it's a 4-component object.
So what's okay?
Right. Okay, so if we do that, then the field equation becomes, well, the field equation from the Dirac Lagrangian is just this equation that we wrote down yesterday, Dirac's equation. Now, when we apply this here, we find the following. Of course, there is an identity here. Almost nobody writes it, but there should be an identity. This is a 4x4 matrix, so it would be silly to write this without the 4x4 matrix. But, well, it's just easy to write it without the identity. So probably I'll stop writing the identity, or now and then, only now and then I'll write it, okay? So we want to give an interpretation for what this M is. So one way to do it is to say, well, if this has to be true, this should also be true, okay? So let's try to give an interpretation. Okay, so if that's true, the following must also be true. I could multiply by the following matrix, the whole equation, and we should still get 0. As I said, I'm not going to write this anymore. Okay, so when we do this, we find kk minus m squared times this guy has to be 0. Okay, now kk, it's written explicitly, is the same as k mu, k nu contracted with the gamma matrices. But I can write this as the anti-commutator if I put a half. And very conveniently, this thing gives us 2 times eta mu nu times the identity. So this thing is k squared times the identity. And therefore, we find that this equation is the same as k squared minus m squared times the identity. Okay, now this is a number, times u has to be 0. So if we want u to be different from 0, then we need k squared to be equal to m squared. And hence the interpretation of this as the mass of the particle.
Should you also define on T?
Should what?
Should you define on T as well?
I'm working in momentum space now, right? And now we see that the 0th component is locked to be related to the other components by this relation. And the relation of this parameter m that we now interpret as the mass. Now, of course, it could have been that m, in the scalar field, we have m squared. Here, it could have been that m was negative, right? Does it make any difference? No, because we can just redefine our fields. Nothing here depends on m being positive or negative. In fact, nowhere in this calculation we're going to see any difference if we set m to be positive or negative. Okay? So, but this is not what we want to do. What we want to do is to solve this equation. So we want to solve yes.
We essentially have an eigenvalue problem with this I bar del minus m. So if m is negative, wouldn't that imply some constraints on whether you can solve that eigenvalue equation or not?
No. No, m is a parameter. And this is the only constraint that I have.
So that makes it obvious that it is mass then?
Yes, that's right.
How? Does k squared equals m squared mean that it should be mass?
So if you have any object that carries momentum, right? Say you have some in your quantum theory, you have some particular state. Remember, in quantum field theory 0, we decided to classify particles by eigenvectors of the momentum operator. Okay? And we also said that one way to classify them was by objects that were invariant under Lorentz transformations. Okay? So one invariant was made by taking the momentum operator square, right? And its eigenvalue was defined to be called, I mean, we gave a name to that eigenvalue, and that name was the mass. So every time you see the value of that operator, the eigenvalue of that operator, you call it the mass square. Okay? So this is precisely what we're doing here. Okay? What other definition of mass do you have in mind?
No, what I meant was like this sort of what from the equations indicates was that this is some sort of inertial property of the part. Like this is a property that gives the part.
Because now we can go to the rest frame. Right? If we go to the rest, that's an excellent question. Actually gave me the idea that we should go to the rest frame. So if you go to the rest frame, what happens to the momentum of this particle? If this has to be satisfied. So it has to be, right? Now, does this equation look complicated or simple? Well, it actually looks simpler than before, right? So now we can use that this actually becomes m times gamma 0 minus the identity in our particular frame. So let's call this k star. Okay. So now we look at the basis and we plug that in here, and we find that the following must be true. In the rest frame, U, this 4-component object, must be a null eigenvector of this matrix. But what is the rank of this matrix? Is what?
Yeah, the second row is at rank 1. Because
Who says that the rank is 2? 1, 2. Very convenient. Oh, 3 now, okay. Okay, 3. Any other ideas? What do you think the rank is?
1.
You think it's 1? Well, oh, maybe because I haven't told you. These are 2 by 2 matrices, right? Now you multiply by 2. Then you get the right answer. The rank is 2. Okay, so that means this is a 4x4 matrix. It means that the core rank is also 2. And that means that the number of, or the dimensionality of the null space must be 2. So the number of eigenvectors yes.
What is your case study?
Rest frame.
Oh, rest.
Okay. Well, now we have to open up Mathematica and then put the metrics in and then ask for the for a basis for the null space. Now, this time is actually easier than that, right? I mean, we don't have to use Mathematica for that. We know that if we have the null space, just has to be something of this form, or is spanned by these options, right? By these two vectors. So this means that we can choose a basis. So let's call this, we can call this U1 and this U2. But actually, it's more convenient to give some normalization and actually think that we should introduce the mass. And this is just a normalization that is convenient for other purposes. And we will define US, where S takes two values, 1 or 2, to be the following. So there is a normalization of the square root of the mass, which now we are assuming to be positive. Okay. It looks silly to introduce these two-dimensional vectors here, or these two-dimensional objects here, but you will see why we're introducing them. It's just for convenience now, but I mean, now it looks silly, but it's going to be useful. Yes?
Is there any particular reason why the normalization is there?
No, the normalization is going to be useful. Well, I'm not sure we're going to get to it, but the normalization will be useful to ensure that the final answers that we're going to get have a nice limit when the mass goes to 0. But it's just normalization. Okay. Very good. So this is usually the trick that you do whenever you want to solve equations of this form. You go to the rest frame, okay? You find the solution, and then you boost. Okay? Now that would be your exercise. To actually use a boost and show that when we boost our rest frame to produce any general vector, then what happens to our spinner, S, so the most general one, has some funny objects here, which I have to define for you what I mean by this. So what do we mean by the square root of a matrix? That's right. You diagonalize, you take the square root of the matrix, and then you go back to the original basis that you had before. So you take the square root of the eigenvalues, and then you go back to the original basis. Okay? Now, part of the exercise not only is to show that under the boost you get this, but also that these objects have a nice normalization condition. I mean, that's part of the reason we introduce a normalization, is that when you take this, you get 2 times the mass times SR. Okay? What do I mean by this bar? That's right. Take U dagger, and you multiply by gamma 0. So is this a number or a matrix? Who thinks it's a matrix? Who thinks it's a number? Okay. Excellent. That was a trick question. It's actually a matrix because it has delta S. Yes. But for fixed R and S, it's a number. Very good, very good. It was a trick question, actually. Yes. Yeah, but for fixed S and R, then it's a number. Yes. Okay. So what happens if we actually write this down in the opposite order? Say we put an S, and we put a bar and an S here. So what kind of object do I get? This is now a matrix, okay? So I'm going to put S and S. I'm going to sum over S from 1 to 2. So let me put, to make sure that we get that we see there is a matrix, let me denote the components by A and B. And then what we find is that this thing is nothing but K slash times M AB. Okay? So this is going to be something important for us. We should keep it in mind. Does this look familiar at all from something that we have done before? Okay, maybe it doesn't now, but
so then we got these objects, the U vectors. You introduced those two-dimensional vectors inside.
Yeah.
That was meant to be a mathematical convenience.
No, at this point it was actually pure stupidity.
Okay.
It would be convenient for what we're going to do now.
And then you boosted them and you get those objects.
Oh, by the way, yeah, so in this case, so from this point of view, it's actually, now it's convenient because you see that the top two components transform like this and the bottom two components transform like this. So yeah, that's right. So on the top board, it was just stupidity, but here it's showing why it was useful. Right?
So what I'm missing after that is like, so for fixed SNR, that is just a number, but now if you fix the S's, would it still not? It would still be a number even now, right?
I mean, this is a 2 by 2 matrix that is multiplying a 2 vector. So that gives you a 2 vector.
2 by 2 matrix multiplying. Okay.
Right?
Yeah.
So this is still a nice 2 vector, and this is also a nice 2 vector.
Yeah.
This is a 4-component object.
Yeah.
If I do the U bar of this with the U, I dot it, and I get a number for a particular RNS. Okay? So now let's study, so we did the positive energy solutions. Now we can study the negative energy solutions. Right, so we did the psi plus. Now we're going to do the psi minus. And here we have to introduce another notation. People like to call these ones V. Okay. So if we follow the same logic, okay, so we plug them into the Dirac equation, and we solve the eigenvalue problem in the rest frame, and we boost, we're going to find that these V's also come in 2 varieties. And there is a minus sign here. And people like to call these vectors eta s. This is just some notation. So that's not very important. And they are also 1, 0, and 0, 1. Yes.
You said these are negative energy solutions. Omega k is negative, right?
So this omega k is defined to be the norm. Yes. That's right. Yes. Yes.
Why are you calling them negative energy solutions?
Because they are negative energy solutions. You?
function of the three-vector case? Is that it? Or is that meant to be
Well, because the 4-vector is not independent. The 4 vectors, the 4 components are locked to have this property.
Okay.
So it was a little bit in using hindsight.
Okay. So you can express either way.
That's right. Yes. And you all know why these are negative energy solutions, right? You went through the struggle that Dirac had, right, when he was dealing with this theory, right? Okay. In other words, we're not doing quantum fields. We're doing classical field theory. And these are negative energy solutions. It's a disaster, right? As in any classical field theory. If you find negative energy solutions, you say, oh my God, this is a disaster. And then we have to get rid of them. But, yes.
This was the reading part of the Q0.
Yes, that's right. It was a tutorial. Yeah, that's right. So you all went through that, and you saw how Dirac had to struggle, and he had to propose this infinite sea of particles and the Dirac Hall theory, all that. But now we know, well, already from the complex scalar field example, right? Well, even from the real scalar field example, we also found Fourier modes that had negative energy. But what did we do with them? Did we get scared? No, we didn't actually get the chance to get scared, because when we thought about this as a quantum field, the real scalar had to be real, right? Or Hermitian as an operator. And that locked the negative energy modes and the positive energy modes, the operators. One of them had to be the adjoint of the other one. So there was a natural interpretation. One of them creates operators and the other one annihilates operators. So in this case, in the case of the complex scalar field, you guys also found the same thing, right? So say the positive energy modes, they annihilate particles, and the negative energy modes, they actually create antiparticles, okay? So the whole problem was resolved. So now we don't have to worry about that. But we have to still work a little bit more before we quantize this theory, okay? So far, we're doing basically what Dirac did, okay? Okay, so the other important formula of this discussion is going to be a formula similar to this. So I'm giving you a chance. Has anybody seen something that remotely looks like this? With a what? Looks like a completeness relation. Exactly. Yes. So with these guys, we will also have the same kind of normalization conditions here, but now with a minus sign. And our master formula over here, which is going to be very important. Okay. Yes, so this is the other one.
What about that minus sign that you have there for particles that,
Which minus sign? What's the problem?
no, I mean, is there any problem with that?
No. Not all minus signs are bad.
I mean, like, kind of having a negative norm.
No, it's not a norm. Why do you think it's a norm? This is a normalization, right? It's a, I mean, but it's not the norm. It's not the norm. We don't have quantum. We don't have quantum states yet, right? So we're not computing norms of particles. Okay, but since everybody wants to see particles, let's actually move on to the quantization of this theory. Okay. So let's actually, well, let's do the only thing that we know how to do, which is the canonical quantization of the theory. So we're going to take our Lagrangian, And just following Tibra's suggestion from yesterday, we're going to write it in a nice way. We're going to split this. Well, let's start with the Lagrangian we had. But now we're going to write it as let's introduce gamma 0, del 0, and then we're going to split the rest. Then what we can do, well, first of all, there is something nice that happens here, which is the gamma 0 that is in the definition of this guy with this, give us the identity. So we can replace this immediately by psi dagger. Okay. So I'm going to use a little trick, and I'm going to write this as half psi dagger psi dot, where the dot means the derivative with respect to time. Okay. And then I'm going to integrate by parts to put the dot here. Okay. Plus the rest. Well, the reason I'm doing this is so that when we compute the canonical conjugate momentum to psi or psi dagger, we get something nice. So if we take the derivative of the Lagrangian with respect to psi dot, what do we get? We'll get a half psi dagger. So this is what we would call pi, the momentum conjugate to psi. And then we can take the derivative with respect to psi, dagger dot, and then we get minus a half I psi. That's right. And this would be pi of psi dagger. Okay. And we're doing all this because we want to compute what? Yes, but why? Yeah, exactly. Very good. So we want to compute the Hamiltonian. Well, first, the Hamiltonian density first. So what is a Hamiltonian density? Well, we'll get our minus the Lagrangian. And if we do that, we just get the term as we would have expected. If we have something that is linear in the time derivatives, we just get everything else from the Lagrangian except that part. So we get psi bar, just the space components. Okay, so that's our Lagrangian density. And now we can proceed to our canonical quantization, imposing equal time commutation relations. So what do they tell us? Well, they tell us that if we take psi A with its momentum conjugate, let's call it B, we should get something that looks like delta 3 of x minus y delta AB. But its canonical conjugate momentum was something that we computed over there. and is basically given by psi dagger. Okay? Well, that looks fine, except that, you see, if for any reason this operator, we could just make it Hermitian, this wouldn't make any sense, right? Why wouldn't it make any sense? Yeah, because this thing would be anti-symmetric, and this thing is symmetric, so it would be a disaster. But maybe it's impossible to make it. Yeah, maybe can we close? Can we also close that one? So very soon we will have kids all over the place knocking. Hopefully we don't have any pumpkins in the door. That would be really funny. Okay, so that would be a little bit funny if these guys could be made Hermitian. In fact, so we already know that they cannot be made Hermitian because this would be a disaster, right? Well, one can keep going and say, well, we could also impose the other relations. And then psi dagger has to be 0. And then we could just proceed along these lines.
So, couple of things.
Yes.
Delta AB is the Kronecker delta.
Yes.
Right? And second thing, X and Y are space-time separated throughout even this discussion.
X and Y here, they have a little vector on top, right? That's my notation for space points. Yeah. But you have to say, no, but that doesn't mean anything. You have to tell me the time. What I'm telling you, the time is t. At time t. And both operators are at the same time, evaluated at the same time. That's why we call these equal time commutation relations.
But you can still have a space-time distance between those two.
These guys are necessarily at a space-like separated. It's not that we can, it's that we cannot not have it, right? The only point in this discussion that is not space-like separated is when x is equal to y, when the vector x is equal to the vector y, okay? Very good. So if we proceed along this line, of course, we're going to keep going and then introduce as usual, creation and annihilation operators for these guys. So these operators with our use will have some annihilation operators. And with these guys, we'll have some annihilation operators and so on, okay? And then we will put this back into these commutation relations to find out what these operators have to do, and we will find that they basically commute. That's what we would find. Okay. But would that be such a good thing for a theory of electrons? What do you think? Yes.
So, before, when we were talking about quantization, the mode amplitude became the creation annihilation operator. So in this case, why do we have a U and an A? Why don't the U's just become?
Oh, the U is like the epsilon in the gauge theory field, right? So we don't want to mix the operator with the wave function of the object, with the polarization part. Yes.
So A's should have some index or something like that, like the field bind thing that we did, right?
Yes, that's right. But it doesn't matter. I'm doing this schematically because that's right. So why wouldn't work for the theory of electrons? Exactly, because these guys will act, the creation operators will act on the vacuum to create particles, say K1 and K2. So they will give us something that is actually symmetric. So we have a wave function that is symmetric. Yes?
Okay. however, in the process we've been making, you haven't seen any relation with or any information whatsoever about the spin of the particle, right? So can't I proceed like this, where I have no information or anything about the statistics?
So you think we haven't discussed anything that has to do? We didn't say helicity.
Yeah, I mean.
Yes. Yeah. So these particles, this object was made out of particles of half-integer helicity, right? Yes.
So a question.
And we are trying to construct a theory for electrons.
Yeah, but okay, we did the
yes.
helicity 1/2 massless particle.
Yes.
Right.
Yes.
So in the case where the mass appears, right?
Yes.
We haven't shown yet that these guys have spin 1/2. Right?
That's right, we haven't. But precisely these two options that we have will become in the non-relativistic limit particles with a spin up and particles with a spin down. So precisely that's the reason we found two things here, okay? But still, our initial motivation was to find a theory of electrons, right? So we say, well, we haven't succeeded. This thing is the wrong theory, okay? So we have to start all over again. But you say, no, wait a second. If this is not a theory of electrons, what is it? Okay? So that's the attitude we should take according to the principle that we should explore every possibility that there is. Okay? We failed to make a theory of electrons out of this, so we should try to study what it is. Okay? So it's an exercise. You can keep going. Okay? Just keep going along the lines that we have discussed. And then you will find that this theory, just defined in this way, will lead to something that violates causality. Okay? So it's not even an option. This theory that we have defined doesn't even exist.
Didn't we sort of, in a way, build causality into it with the commutator?
No. Last time, remember, we're actually, when we do canonical quantization, remember, in the first week, we said that canonical quantization does violence to Lorentz invariance, right? Yeah. So we really have to check that we have causality. That was something we had to check. So I'm telling you that if you keep going with this theory, you will find that it's impossible. You will violate causality. Okay?
Can you give a rough argument of why this is the case?
That's your exercise. Just sit down and do it. You will gain much more from doing it than from me telling you what it is. You will probably forget it next week. If you do it yourself, you will probably remember it for much longer. Okay. So what do we do? Well, this is a point that the next step doesn't take skills, it takes inspiration. Okay? So it cannot just, it just has to be done with inspiration. So the next step is to say, well, replace commutators by anti-commutators. Well, part of the inspiration can come from the fact that you want a theory of fermions, right? You want to have Fermi statistics. So if commutators gave us a theory of bosons, then anti-commutators might have a chance of giving us a theory of fermions. Okay?
And does this work throughout, like as a general principle? Always?
Yes, and that's called the spin statistics theorem, which we're not going to prove. So what do we want to do? We want to impose that this is true. But as I'm writing this, now that I have done, I'm done with this, I'm going to write the next one with the daggers. But while I'm doing it, I want you to think why this still looks like something that violates causality. The answer is much simpler than actually computing what we had to do in the case of the scalar field. Okay. It's just looking at this object. So remember, what did we say? Just a second. Remember, what did we say about the condition? What was the condition that we had to impose on operators to have causality? Exactly. Very good. Now, they don't even commute. Isn't that a disaster? So we tried to fix a problem because this theory will not lead to something that has causality. And we seem to have made the problem even worse.
If your observables depend on powers of psi, doesn't that imply that those powers are zero?
Exactly, that operators cannot depend on an odd number of fields. So that's the resolution to the causality problem. On an odd it cannot depend on an odd number of them.
It depends on
the observables. So to have a chance of having causality, okay, implies that an observable can only be a function of an even number. Okay?
Can we go through why that is of why we can see that from the anti-commutation equations?
Oh, because if the psi's themselves, if these operators were observables themselves, right? I'm already telling you that at the same time, right, at space-like separations, they don't commute. So if the observables don't commute, I can make an experiment, measure this guy here, and affect what is going to happen somewhere else, which is a space-like separated from me.
Yeah.
And that's a violation of causality.
Yeah.
Okay?
I meant like, why?
Oh, why this fixes the problem?
Why? So now that, yes, why is this
Well,
function of
because now, if you take a function that depends on an even number of fields psi, guess what? That function, at least at equal times, say you have one operator and you have another one, they commute. Of course, I said that causality, implying causality or requiring causality implies this, but we have to work even more to show that this theory actually makes sense, okay?
One little question.
Yes.
Is there any fundamental reason why we're using psi dagger instead of psi bar?
Yes, there is, because it was here. We're doing canonical quantization, right? So we had no choice. We had to compute. We had to use the... Here, I should have used pi, really. I mean, that's the origin of that formula.
By treat, instead of taking the psi dagger, you just psi bars, the commutation relation would change a little bit with that commutation relation.
I mean, of course, if you prefer, you can put a bar and change this accordingly.
But anything, I mean, everything will be the same.
No, the canonical quantization has to be exactly what I told you, right? That's the procedure for canonical quantization. You can say, why are we doing canonical quantization? But that would be another question, right? Yes.
So if you have an even number of fields, then that always equals 0, right? So have like psi squared or psi to the fourth and not always be 0. So it seems like.
Well, they don't have to be the same field. Okay, we can have a psi, and we should try to make. We will soon see that there are. We will soon see what observables we can find in this theory. Okay. Very good. Okay. Another clear problem with this is, well, we seem to have evaded this one by just saying that, well, whatever is a problem, we don't use it. Meaning operators that don't commute, we just don't use them as observables. But there is another funny issue. What happens in the classical limit? What happens in the classical limit in the regular scalar field? What happens to our operators? What do they become? Now, all the commutation relations, right, become trivial. Everything commutes. And then people like to say that they just become numbers, right? These operators are now can be represented as numbers because the commutation relations are trivial, okay? In the classical limit, this will also drop. And now we say that, oh, okay, so all these fields can now be represented nicely by objects that completely anti-commute. Well, luckily, somebody studied that before. And those are called Grassmann numbers. Okay? So in the classical limit, our fields actually become Grassmann numbers. So we have to be careful. And everything we did yesterday, you should reconsider everything we did. And now remember that in the classical limit, these objects are actually Grassmann numbers. Okay? Of course, the representation theory we did was completely fine. The Lorentz group still has its left-handed spinors and right-handed spinors. And the spinors we found are vectors made out of complex numbers. So that's completely fine. But what we have to remember is that when we use them in a Lagrangian to build a classical field theory for these objects, we have to use, or we have to remember that they are Grassmann objects. Okay? Very good.
Is there an easy way to see that they're not like the usual number?
Well, because they anti-commute. They fully anti-commute.
Okay,
they have to be represented by a new kind of algebra. They cannot be represented by the standard field of complex numbers. Okay? Okay. So now we are ready to write the field psi in the way that you all want to see it, because it's a standard way that we wrote it, not in the schematic way that I was doing there. Now, there are several conventions out there. Some conventions, this is called B and this is called C. I guess the reason is that some people don't like to call this A so that you don't confuse it with the annihilation operator of a scalar field. But this is a notation that Peskin uses, and so let's follow that convention because probably many people use it. Okay. So now this looks more familiar, right? This actually resembles the expansion we had for the photon field, right, for A mu, where we had the polarization vectors, and we had creation or annihilation operators for each one of the polarizations that we could have. So here we have an annihilation operator and a creation operator for each of the choices that we can have, okay, for the wave functions of our field. Now, it's a matter of putting this back into these anti-commutation relations. Okay, let's call this star. Now, using a star, again, as we did for the scalar field, you can show that the A's satisfy anti-commutation relations. And these are exactly the same as the B. That's what the B does. Okay? And everything else anti-commutes. Okay? All other possibilities give you 0 for the anti-commutator. Okay. So now we can go back to our Hamiltonian and ask what the Hamiltonian looks like in terms of the creation and annihilation operators. Now we're going to study the Hamiltonian and not the Hamiltonian density, so we have to integrate our space.
Sorry, Freddy, are we missing an I in the commutation relations website?
Now we have to be careful because remember the anti-commutation relations, or what they were supposed to be, were with the canonical conjugate momentum pi, and there is an extra I when we define it with the psi. Okay. Very good. So here comes something interesting. Remember that this was the painful part of week 1, right? Well, at least the first pain we had. I mean, we had many, but this was the first disaster that we encountered, right? The reason was that when we did this, we found the following. We found something that looks like this. And here, well, we didn't find this, but if we have several creation and annihilation operators, it makes sense that we're going to sum over them. Okay? So we found something that looks like this. Okay? And this was the time when we said, well, if we want to compute the energy of the vacuum, so we define a vacuum such that it's annihilated by all possible annihilation operators. Then to compute the energy of the vacuum, we had to flip these guys using the commutation relation in this case of the scalar. But here, what we have to use are the anti-commutation relations. So can anybody see what's going to happen? Still looks like a disaster, but what kind of disaster? Well, we have minus Bs let's pretend for a second that they are at different momentum, okay? And we want to write this as Bs dagger. Sorry. And what do I have to put here? If you look at the anti-commutation relations. Well, if this guy was on the other side, it would be minus the anti-commutation relation that we have there. So we'll have to put here a minus delta 3 of k minus k prime. Okay? That looks still pretty bad, but let's keep going. So the Hamiltonian now has an integral d3k omega k, something nice, which will completely annihilate, which will give 0 when you apply it to the vacuum. So this part will not compute anything for us. I mean, will not give us any contribution to the energy of the vacuum, but there will be an extra term, and that extra term is minus integral d3k omega k times this guy evaluated when these two things are the same, because that's exactly what we need. So we still get minus delta of 0, which, if you remember, this is in momentum space, and therefore is an integral over all space-time. Okay? So we get our minus delta 0 here. So what's the difference between this computation and the answer we got when we did the scalar field? There is a minus sign. So fermions contribute to the vacuum energy with a minus sign. Yes? Exactly. You get twice that contribution from summing overs. Yes. Very good, thanks. So, I mean, it's really hard to avoid the temptation of saying that the two disasters can combine, right, to actually give you something sensible. In fact, if you had started with a theory that had, say, two scalar fields, two real scalar fields, and this guy, then together, they will give you something, of course, if you can combine these infinities. Of course, I know some people here don't like adding infinities and dividing by, but if the two infinities are identical, then you can cancel them. Now, for them to be identical, what do you have to require? What? The same mass. So the two must have the same mass. Otherwise, this infinity will not be the same as the other infinity. So in order to cancel this infinity, you probably have to have, for each particle that you have of a given mass, you will need somebody else with the same mass, but with the opposite statistics. And that looks like a complete disaster. We don't see that happening in nature, okay? But still, it's very tempting to say that something like that could happen. So perhaps some sort of cancellation between bosons and fermions could solve the cosmological constant problem, okay? We don't know. Is this what? Is a way of what? Not really, because we know that at our scales, when we perform experiments, the particles we see don't quite satisfy this. And even at the experiments we have done at the LHC, particles don't satisfy these kind of cancellations. But perhaps, of course, remember we said the cosmological constant problem is really bad, even by assuming that we only get a contribution up to the energies we have measured, right? But somebody could say, well, what if we build an accelerator that is 1 million times more powerful? So the problem could actually get worse and worse, right? Now, it could be that at some point, the problem is so bad that even nature doesn't like it. And it would say, no, we have to fix the problem at some point. So maybe at very, very high energies, there could be some cancellation that happens like this, that when you go down in energies, for some reason, these half of these guys disappear or become very, very massive. And the degeneracy that you need for this to happen will break down, and we don't see that our energies. But certainly this doesn't seem to be a mechanism right now to solve the cosmological constant problem, because at the energies we see, we don't see anything like this happening. But it's actually very tempting. And we say, oh, please, we know there are fermions in nature. I mean, the electron is a fermion. So it would be really a pity when you say that there is a minus sign over there. But we need young people with bright minds to actually figure this problem, because many people have tried and nobody has succeeded. Okay. Okay. So let's move on to the Hilbert space. So we already started with the vacuum. So of course we can create now particles, or we can create states that we will interpret as particles by applying, say, creation operators. And this object will give us, then let's actually jump ahead and call it an electron, say. If not, it's the next letter that we can use, right? We use A, B, and C was the speed of light. And so we have this. Okay. Of course, we then find that this will have to be minus So this quantization procedure seems to lead to something that makes sense as a theory of fermions.
The handedness has disappeared in the discussion somewhere along the way, and I don't understand why or how.
No, it's here. So as I told you, the different values of S will correspond to spin up and spin down. Okay. Now, right-handed or left-handed doesn't make any sense because this is a massive particle, and whether you have something with helicity plus or minus, as helicity being the projection of the spin of the particle along the direction of motion depends on your frame. So that notion is not very useful when you have massive particles. When you have massless particles, that's completely fine. And it's actually what we found in quantum field theory 0 as a Lorentz invariant. Okay? Yes?
So the anti-commutation relationships are symmetric between A and A dagger. When did A daggers become the creation operator and the A's become the NID?
Well, you could ask the same question in the scalar field theory, right? And it's exactly the same answer. These guys, yeah, that's right. So these guys will now create particles with positive energy. Okay? That's a guy. Okay, very good.
That convention is opposite to like what we read up there, as in we said that the A daggers are connected with the B's, which are connected with negative energy solutions.
No, here in the, where did I write the nice, okay, here, I think. This is exactly the convention we had for the scalar field.
Right. I guess we can use both cases.
No, so the modes for this guy are interpreted as the ones that annihilate particles, right? Okay. So what do we need to actually start doing some calculations with this theory? What do we need? Feynman rules, yes, that would be very desirable. But before we get to Feynman rules, what do we need? We need interactions. But even before we get to interactions, what do we need?
Propagator.
Exactly, we need a propagator. Okay. So how do we get a propagator here?
You define the state of your Hilbert space by acting with A dagger or B dagger, right?
Yes.
But the anti-commutation relations imply that I cannot pass the state with I mean, with acting of A dagger and B dagger, right?
Why not?
Because if I have the anti-commutator of A dagger, B dagger is 0, right? Then
Yes.
Does that imply that A dagger, B dagger is 0? Okay. Okay.
If you have exactly the same energy.
Okay. Okay.
Okay. So we need a propagator. Okay. So one possibility is to actually sit down and derive it, right? And how do we derive the propagator? Well, we should try, sit down and compute. Remember how we did it for the scalar field? We would actually compute 2-point functions, or meaning, yeah, that's how we call them, 2-point functions of fields. Say this with this, or we could compute this. And here it's actually more convenient to use a bar. I mean, it's the same because I'm just labeling a component, so it doesn't matter. And we could go on and compute all these guys and define this object to be remember this little symbol from week 1? That seems like a long time ago. Even week 2, I think, we did some of this. Yes. And we could also have this guy here. And we have a contraction, okay? Well, this wasn't quite this. This contraction was actually what? Yes, that was the name, but in terms of an expectation value, what was this? Yep, it was a time order guy. So this thing was actually connected to the time order. And this guy should also be connected to some notion of time order. But what do we mean now by time ordering, right? These objects anti-commute, okay? So certainly if I write it like this and I say x0 is greater than y0, no problem. But what happens if y0 is greater than x0? Should I put a minus sign? Should I allow my t operator to just fix the guys without putting a minus sign? What do you think? Is the t operator going to be powerful enough to completely erase the minus sign? It's actually not erased this. I said it and then I did it. It's amusing. Okay. Yeah. We could try to be democratic and have a vote, okay? So who thinks that the time operator should be allowed to do whatever it wants, regardless of what kind of fields we have? Okay, let's actually not allow the time operator to do anything, but let's actually try to define something that is useful for us, okay? So the propagator.
Explain what you meant by the minus sign appearing. Where does it appear?
Well, the time operator, if y, imagine that y was y0, the time y0 was greater than x0. Okay. What is the time operator supposed to do? The time ordering operator. It's supposed to fix that and say, well, the guys that happen last should be to the left, and the other ones Yeah, but now and then, should we just put it, or should we put a minus sign because they anti-commute? Oh, yeah, that's a problem.
However, I mean, can we just take the same definition of the time ordering operator and be more careful whenever we pull it out and have a product of operators? When we have, for example, this endpoint function with the interaction, right? That was this series, and you pull out the time ordering operator and you just say everything commutes, and the time ordering operator will fix everything that we didn't have into account, right?
Well, we could try to guess, but let's actually think about what the propagators did for us. You remember there was a tutorial where you found that Feynman propagators had a very interesting meaning from the point of view of the differential equations that we were trying to solve. What was the meaning of the Feynman propagator? They became the Green's functions, okay? So let's see if with the Green's functions, we can actually make more sense of what we're doing. So let's review first the case of the scalar field. But now, okay, let's start with this. So this was the Klein-Gordon equation. Now to find the Green's function, we had to solve this equation. And I think there was a convention. We had to put a minus sign here, right? So when we go to momentum space, so the trick to solving this is just to go to momentum space and solve the equation in momentum space where it becomes algebraic. So if this is the case, then the equation we have to solve is minus k squared plus m squared equals to minus I. And from here, we conclude that this was I over k squared minus m squared. Of course, we now see that if we plug this in here, we have to make a choice of contour, because just as given, it's not well defined, because the poles are exactly located on the integration region. So that's the point where we put an F in the Green's function, because Feynman gave us a prescription for choosing the contour. Actually, he was even smarter. Instead of telling us the contour, he moved the poles and kept the constant, the contour fixed. And we had this. So this is what we had in the case of the scalar field. Now what happens if we have several scalar fields? Say that we have several scalar fields, right? Many species of scalar fields. Then our Green's function should actually depend on what particle we create at one point and one particle we annihilate at the other point. Of course, in the case of the scalar field, this is trivial. We just put a delta ij. Okay? So if you put a delta ij there, we just have to keep putting it everywhere. And then the equation is ij delta ij. And the last modification we have to make is putting it there. Okay? This is starting to look like the Green's function we found in the case of the photon field. Okay. So the next case that we studied was the photon field, and there the equation was even simpler. Right? So the Green's function equation would have been, now we have an index, okay? So the Green's function must have two indices. And we get, if we have a space-like components, we should get something that looks like the scalar field. And that's what motivates us to put a minus eta mu nu here with delta 4 x minus y. Okay. So this is the analog of the yellow guy that we have over there. And when we solve this, now as a function of k, we find, not surprisingly, this propagator. Okay? So now we just have to do it for the Dirac equation.
How do we know that in this propagator we are, I mean, with the eta mu nu, we built in the random property into the propagator. But the delta ij was just 1, 1, 1, minus 1, minus 1, minus 1, 1, 1. So, isn't, I mean,
yeah, that's why you need the minus sign.
Okay.
Right? So finally, let's do it for the Dirac field. So what's the equation we have to solve? Well, the equation we have to solve is the Dirac equation. So what's the Green's function equation? Remember, now this is a matrix. Yeah, that's right. So we have this matrix. This is a matrix AB that is multiplying something, okay? And what it's going to be multiplying is another matrix, another 4x4 matrix. And we want this to give us the minus sign is just a convention, really. Because remember, this operator, yeah, the minus sign is just a convention. Okay, so we want to solve this equation. So what do? We go to momentum space again.
But won't we have problems with consistency if we're using that convention there on that?
No, we just have to check what this is. You will see what's going to happen. So let's go to momentum space. So in momentum space, our equation looks like okay, looks pretty good. Can we solve it? Well, this is a matrix, right? So what do we have to do? Exactly. So S is nothing but I over sorry? No, S is a matrix, right? S tilde is a matrix. And so is K, yes. So what do we mean by 1 over a matrix? It's the inverse of that matrix, right?
Freddy, are you missing factors in 2i possibly?
Sorry?
Are you ignoring factors in 2i? Just pick up another one to the delta function.
There are no factors of 2 pi here, but they will be in the definition, in this definition, right? In the definition of the delta function, there will be factors of 2 pi. Yeah, but this will be the answer if you take into account the factors of 2 pi. Well, I mean, this is just the inverse of the matrix. I mean, and people like to write it like this. But this doesn't look like something terribly useful, right? Can we compute the inverse of that matrix? Well, let's look here on this blackboard. That's why I kept it. Look at this equation. Erase this. Erase this. We found that this was equal. Oh, yeah, I didn't put it. So it was kk. So this was equal to this, and this we found was equal to that. A number times the identity, which is 4 by 4. So this guy, which is the object we're seeing over there, if we multiply by this matrix, we get a number times the identity. Well, we should call the inverse of this guy this divided by this. Yes?
But didn't we say that k is equal to m? And that's 0.
K is a matrix, cannot be equal to m. What we said was that k squared,
so
the number.
You end up with a number times.
Exactly. That's very good. That's when we were solving the equation, right? Yes. But we are only supposed to use this propagator.
When it's off shell.
Yeah, I don't even like to say off shell, but yes, we're only supposed to use that propagator for the internal lines, right? The LSZ formula told you to remove the guys from the exterior, okay? But this derivation didn't assume anything, right? So precisely, we did this in order to find this as an on-shell condition. But as a matrix, this derivation we did is perfect. So we just got this, and therefore, the inverse is, we just get I, k plus m divided by k squared minus m squared. And now we put the I epsilon in order to have the Feynman condition. Okay, see what time is it? Very good. Now we go back here and we ask, is there any prescription that will give rise? So what we want, this to be equal to that object that we found over there. Okay. Yes. Okay. Yes. That I chose?
That you assigned the propagator to be precise and bar instead of precise sign.
Yeah, well, it's more convenient to use it like that. It's just really, I don't really like it when people write these formulas with the whole thing without putting the indices. I prefer to put the index. And by this, I mean the component B of this object. So you can easily compute it in terms of psi dagger if you want, if you prefer, okay? But it turns out that this is, using the bar is a nice definition to connect it to the propagator.
So that defines the time order.
Yes. So what is the definition that gives rise to this? Now we will know the answer to the question we posed at the beginning, which is, what is the definition of this object? And the definition is, last time to guess. So what gives rise to this So in other words, if you compute, so if x0 is greater than y0, you can close this contour. There is only one choice to close this contour around infinity. And when you do it, you find exactly what you would get if you did this computation. Not surprisingly, everybody guessed that part, right? Now, if y0 is greater than x0, then what you find is minus this. Okay? So the time ordering operator has to remember that these objects anti-commute and put a minus sign. Okay.
Does psi vanish? Like
yes, that's right. So we don't have propagators for psi or psi bar, psi bar. Let's see, is this? You see, I usually save the back guys at the back for last. So in the last 5 minutes, let's use what we have learned to fix one of the theories we studied. What do you think is a theory I want to fix? There was a theory that you guys studied in a tutorial, so I'm giving you hints. And in the lecture, we actually did some of the Feynman diagrams and we computed some of the scattering amplitudes. Exactly. The theory of nucleons. Remember why the theory was funny? Why it shouldn't have been called nucleon, really? I had to put quotation marks. Well, the reason was that the nucleons are known to be fermions, right? And we pretended that they were complex scalars. But now we can fix that problem. And in fact, this is a very famous theory. It's called Yukawa theory. And what's a Lagrangian? Well, we need a Dirac fermion to describe the nucleons and the antinucleons with some mass m. And we need a scalar, a real scalar, to describe our meson field, just as we had before, with some mass little m. What do you think the interaction could be? Well, once again, it has to be a Lorentz invariant. And we want to write down the simplest possible one. In fact, by counting dimensionalities, this is the simplest interaction we can write down. And this is called a Yukawa coupling. Okay? So like we did, so what are the Feynman rules for this theory? Well, we denote, as we did last time, by a broken arrow or a dash arrow, a dash arrow or a dash line, the propagator of the scalar, of the meson field. Okay? Just to remind you, these things, just as we discussed there, come from the contractions in the correlation functions. When we use Wick's theorem to evaluate the correlation functions in coordinate space, then we went to momentum space, and then we used the LSZ formalism to get Feynman rules for the scattering amplitudes. So now we have the propagator for our nucleons okay, and these ones represent these contractions. Or came from these contractions, but now in momentum space. And last but not least is the interaction okay. Now we are exactly in the same situation as we were when we studied the meson electrodynamics. Do you remember the problem we had back then? The problem we had was that we knew how to compute any scattering amplitude where the external particles were mesons. And the internal particles could be photons. And here, we seem to be in the same situation. We know how to compute any scattering amplitude where the external particles are our mesons. But what do we do when we have nucleons as external particles? Okay? And that's what we're going to discuss tomorrow. But let me give you a hint. And you can try to think about this using our thought experiments. And the hint is, well, we need rules for external nucleons and antinucleons. And that reminded me that there is a little bit something here I have to tell you, which is that here the momentum is k in that direction. What happens if I reverse it? If this k is, if instead I draw a line where the momentum is flowing in the other direction, if I did it here, nothing happens. But if I do it here, guess what happens? Yeah, so it seems that we need another rule, which is that if you have this guy with a momentum going in that direction, then you get I minus k plus m. Oh, this m should have been the capital M, right? This is a capital M plus I epsilon. Okay? Well, the reason I remember that I should have told you that is that the hint uses both things. So use, I kept them precisely for that purpose. So what a better way to finish a lecture than to use the strings, pull some strings, and say that this is one of the hints. Look at this. Put it in here. Use our little trick of modeling the interaction of the actual experiment. Okay? And what is the other one? I know I kept it. Is it here? Ah, here it is. So you guys guessed correctly that this guy was a completeness relation, and it reminded you of the completeness relation for the polarization vectors. So go back to your notes and see how we derive the Feynman rules for external photons by using our thought experiment and the propagators. And repeat the same exercise, now remembering the arrows, that the momentum changes the propagator. And the same thing here, okay? To give rules, so use the two formulas we circle to find rules for what happens when we have a nucleon incoming, a nucleon outgoing. So let's call it, now we can call it N, because it's really a nucleon, and a nucleon, antinucleon incoming, and an antinucleon outgoing. In all those cases, you will find different things that you have to use, okay? So that's what I want you to do before the lecture tomorrow. Let's stop here.